Section 1 Introduction. Let's dive into the world of generative models, a powerful type of machine learning model that has a wide array of applications, from creating art and music to advancing medicine and physics. These models are designed to learn and mimic the underlying probability distribution of a given dataset, and can generate new samples that resemble the original data. They can be used for a variety of tasks, such as creating synthetic datasets to increase the diversity and scale of training data, or for unsupervised learning, where they can discover patterns and hidden structures in data. One particular type of generative model that has shown great promise is the diffusion model. These models work by refining data iteratively through a process that builds up the data step by step from pure noise. For training, a process is introduced that progressively adds noise to the data. The model is then optimized to mimic this process. However, a key limitation of most existing diffusion models is that they rely on a fixed process that can't adapt to the specific task or data at hand. In this paper, we introduce Neural Diffusion Models, NDMs, a new framework that allows for nonlinear, time-dependent, and learnable data transformations. We construct a general process as a sequence of latent variables, each of which is created through a transformation of the data, to which we then add noise. This is then used in the corresponding reverse process. To train NDMs efficiently, we generalize the diffusion objective while keeping it a bound on the log likelihood. We also derive the time-continuous version of the objective function as well as the corresponding stochastic and ordinary differential equations for the reverse process. We show how NDMs can generalize several existing diffusion models and propose a new model with learnable transformations of data, parameterized by a neural network. We provide experimental results on synthetic data as well as on several image datasets. NDMs consistently outperform baselines in terms of negative log likelihood, and for a small to medium number of steps, they achieve better image generation quality than denoising diffusion probabilistic models, while being comparable for a large number of steps. We also demonstrate that unlike conventional diffusion models, NDMs allow learning simpler generative dynamics like dynamical optimal transport. Our contributions can be summarized as follows. 1. We propose Neural Diffusion Models or NDMs, a new framework that generalizes conventional diffusion models in both discrete and continuous time settings. 2. We develop an objective function to optimize NDMs that upper bounds the negative log likelihood and study its properties. 3. We demonstrate the utility of NDMs with learnable transformations in terms of consistently improved log likelihood and for small to medium number of steps improved generation quality. Diffusion models are generative models that use latent variables. Given a sample from the data distribution, we define a process that produces latent variables. In contrast, the reverse generative process reverts this process, starting by first generating the same latent variables and then data. The standard approach to specify this process is as a linear Gaussian Markov chain. However, we can also use an implicit definition of the process. To construct the implicit process, we first define the marginal distributions. Using these marginal distributions, we can define the joint distribution of all latent variables. In general, the process is considered fixed and has no trainable parameters. Moreover, it is specified in such a way that the initial and final distributions are approximations of the data and a normal distribution respectively. However, the distribution depends implicitly on the data distribution and thus has a complicated form, so we instead approximate the reverse process using a Markov chain with a certain distribution. The combination of the forward and reverse processes is a form of variational autoencoder. Therefore, it can be trained by optimizing the usual variational bound on the negative log likelihood. In the case of diffusion models, it can be written as a sum of Kullback-Leibler (KL) divergences between posterior distributions in the forward process and the distributions from the reverse process. In the general case, this KL divergence is intractable, so the standard choice here is to set the marginal conditional distributions to be Gaussian. Finally, the reverse distribution is set to be the same as the forward distribution, where the model's prediction of the data is used. Since both distributions are Gaussian, we can compute the KL divergences in the diffusion term in closed form. This choice of forward and reverse processes, resulting in analytic expressions for the diffusion terms given data, is what makes diffusion models a simulation-free approach. Simulation-free means that we do not have to sample all latent variables for each optimization step. Rather than calculating all individual terms in the diffusion term, we can uniformly sample a time point and optimize only a subset of KL divergences using stochastic gradient descent. Furthermore, as demonstrated, when the number of steps in the denoising diffusion probabilistic model goes to infinity, we can transition to continuous time. In this scenario, the reverse process can be described using a stochastic differential equation. This formulation allows us to switch to the equivalent ordinary differential equation and to use different solvers for sampling and density estimation. Section summary. Generative models learn to mimic the probability distribution of a given dataset and can generate similar samples. However, most existing diffusion models rely on a fixed forward process, limiting their adaptability. In this paper, we propose neural diffusion models, NDMs, which allow for nonlinear, time-dependent, and learnable data transformations. NDMs outperform baselines in terms of negative log likelihood and image generation quality, and also enable learning simpler generative dynamics. Section 3. Neural Diffusion Models. Let's delve into the concept of Neural Diffusion Models, NDMs. These models can be seen as a unique kind of hierarchical variational autoencoders. In these models, we determine the hidden variables by scaling data points and adding Gaussian noise. However, this approach restricts the flexibility of the hidden space in diffusion models, which hinders the learning of more useful distributions for the reverse or generative process. To address this, we suggest a more general form of data transformations that allows us to define and learn distributions of the hidden space. We present the Neural Diffusion Models, NDMs, a framework that doesn't require simulation and extends traditional diffusion models. The central concept in NDMs is to apply a transformation that changes over time to the data at each step of the forward process before adding noise. Previous diffusion models are special cases where the data transformation is either linear, doesn't change over time, or is a predefined nonlinear transformation. In contrast, the NDM can work with any transformation of data that changes over time and can be learned from start to finish. We'll later provide experimental results with this transformation parameterized by neural networks. Let's define the NDMs in a constructive manner. First, we define the desired marginal distributions. Here, we have a function that applies a time-dependent transform to the data point. We adapt the approach from DDIM, as described earlier, and choose a posterior distribution that satisfies certain conditions. Using this posterior, we can define an implicit forward process. This forward process provides access to both marginal and posterior distributions just like in the DDIM framework. The corresponding NDM variational objective has a specific form. While the objective has the same form as in DDIM, the individual terms are different. If the transformation is actually parameterized by learnable parameters, the prior term and the reconstruction term depend on the parameter as well. Therefore, in that case, these terms cannot be excluded from the optimization process. For the standard parameterization of the reverse process through approximate posteriors, the KL divergences in the diffusion term are calculated in a certain way. Note a distinction between the objectives of NDM and DDIM here. In the case of DDIM, the model tries to accurately predict the data point. In contrast, NDM aims to predict the transformed data point. Despite this change, NDM's optimization remains simulation-free, so we can efficiently train the NDM by sampling time steps and calculating corresponding KL divergences. Given that NDM is a generalization of DDIM, we can leverage the same techniques for inference. Specifically, we can adjust the number of intermediate time steps, the schedule of a certain parameter, as well as sampling with various dynamics, including a deterministic dynamic corresponding to a certain condition. Section summary. Neural Diffusion Models, NDMs, are a framework that extends conventional diffusion models by allowing for any time-dependent transformation of data. By applying a time-dependent transformation to the data at each step of the forward process, NDMs can learn more useful distributions for the generative process. The NDM variational objective includes terms for the prior, diffusion, and reconstruction, and can be efficiently trained by sampling time steps and calculating KL divergences. Section 3.2 Continuous Time NDMs. In the previous section, we discussed Neural Diffusion Models, NDMs, in a discrete time setting with a specific number of steps, t. However, we can also apply these models in a continuous time setting by allowing the number of steps, t, to become infinite. In this scenario, the time steps, which were previously discrete values from 0 to t, now become a continuous range from 0 to 1. The diffusion term of the objective then simplifies to an expectation over time. The mathematical expression for the diffusion term in continuous time involves several variables and functions. These include the time-dependent functions alpha, sigma, and g, as well as the partial derivative of the transformation function f with respect to time. The expression also includes an expectation over three variables, x, u, t, and z, t. The details of this expression can be found in the appendix of the paper. Training a continuous time NDM is similar to training a discrete time NDM and involves sampling time. In our experiments, we used a method called importance sampling and sampled time from a distribution that is inversely proportional to the square of the function g, t. The reverse process, which was discrete in time, also becomes a continuous process, described by a stochastic differential equation, SDE. By changing the function nu, t, we can obtain different dynamics. In the extreme case where nu, t, is a constant, we have deterministic dynamics described by an ordinary differential equation, ODE. This allows us to use SDE or ODE solvers for inference and to estimate densities by considering the model as a continuous normalizing flow in the deterministic case. In the next section, we present empirical results for the proposed neural diffusion models with learnable transformations on synthetic datasets as well as multiple image datasets. The results show that NDMs learn transformations that simplify the data distribution, leading to predictions that are more aligned with the data. NDMs consistently outperform the baseline in terms of likelihood and achieve better image generation quality than DDPM for a small to medium number of steps. We demonstrate NDMs with learnable transformations on the MNIST, CIFAR10, downsampled ImageNet and Celeba HQ256 datasets. In all experiments, we use the same neural network architectures to parameterize both the generative process and the transformations. We use the UNet architecture for experiments with images and apply horizontal flipping as a data augmentation technique for training models on CIFAR10 and ImageNet. We use the DDPM variance-preserving schedule of noise injection for alpha, t, and sigma squared, t. For density estimation of discrete data, we use uniform dequantization. We report negative log likelihood, NLL, in bits per dimension, BPD, negative evidence lower bound, NELBO, and sample quality as measured by the Frechet inception distance, FID. We calculate NLL by integrating the corresponding ODEs using the RK45 solver, and both NLL and NELBO are calculated on test data. For FID, we report the score averaged over 50K images. Section Summary. In this section, the authors introduce continuous time neural diffusion models, NDMs, as an extension of the previously formulated discrete time NDMs. By allowing the number of steps to go to infinity, the authors transform the set of time steps into a continuous range and derive the diffusion term of the objective as an expectation over time. The authors also discuss the training process for continuous time NDMs, which involves sampling time from a distribution proportional to the inverse of the diffusion term. Additionally, the authors describe the continuous time reverse process, which is described by a stochastic differential equation, SDE, and mention that different dynamics can be obtained by changing the function nu_t. The authors present empirical results showing that NDMs outperform the baseline in terms of likelihood and achieve better image generation quality than DDPM for a small to medium number of steps. They also demonstrate the ability of NDMs to learn simple generative trajectories. Section 4.2 Learn Transformations. Let's delve into the transformations that our model, the Neural Diffusion Model, NDM, learns. We'll look at three different datasets: a 2D checkerboard distribution, the MNIST dataset of grayscale digits, and the CIFAR10 dataset of color images. For the checkerboard, our model learns to change the interwoven pattern into a non-interwoven one. When it comes to the MNIST dataset, the model learns to emphasize the unique features of the numbers, making the lines thicker and even creating bubbles at the corners. For the CIFAR10 dataset, the model learns to enhance the contrast of the images. In all these cases, the model simplifies the data distribution, which could make it easier to transition from simple to complex distributions in the reverse process. We also want to highlight the difference between the predictions made by our NDM and the denoising diffusion probabilistic models, DDPM. We trained both models on the MNIST dataset and generated predictions based on samples from a standard normal distribution. While we don't expect these samples to be of high quality, the predictions made by our NDM are much closer to the actual data distribution than those made by the DDPM. This is because our model aims to predict the transformed data point, not the original data point. This means that any deviation from the original data distribution is amplified by the transformation, making it less likely to occur in the NDM's predictions. Next, we quantitatively evaluated the NDMs with learnable transformations. We trained the model on the MNIST, CIFAR10, and downsampled ImageNet datasets. The NDM performed comparably to the baseline models on the CIFAR10 dataset and outperformed them on the ImageNet dataset. We also compared the NDM to the DDPM on the same datasets, using the same objectives and hyperparameters for training. The NDM consistently outperformed the baseline on all datasets, especially when fewer steps were used. This improvement is likely due to the NDM's ability to fit the distributions of the forward process and simplify the denoising task for the reverse process. However, when we reduced the number of steps used for sampling, both models performed worse, with the NDM showing a more significant degradation. This was particularly noticeable when we reduced the number of steps from 1,000 to 10. While the NDM can work with a reduced number of steps, it is less robust to such changes compared to the DDPM. We also found that the NDMs can be successfully combined with the linear spectral Gaussian mixture model, LSGM. In this experiment, we replaced the linear diffusion in the LSGM baseline with NDMs featuring learnable transformations. The NDMs showed better likelihood estimation and sample quality. In theory, we can view the diffusion model as a hierarchical variational autoencoder, VAE. The conventional diffusion model can be seen as a VAE with a fixed variational distribution, while the NDMs with learnable transformations can make this distribution learnable. This effectively reduces the gap between the log likelihood and the variational bound. In practical terms, the learnable transformation function tends to acquire a transformation that makes it easier for the reverse process to fit the forward process. This gives us additional flexibility in defining the reverse process. However, it's hard to say what the transformation should be in general, as it may learn anything that fits the reverse process. Despite this, NDMs with learnable transformations provide better likelihood estimation and additional flexibility in defining the reverse process. Section Summary. The NDM model learns transformations for different datasets, such as converting an interleaved pattern into a non-interleaved one for the checkerboard dataset, highlighting distinctive features of numbers for the MNIST dataset, and increasing image contrast for the CIFAR10 dataset. These transformations simplify the data distribution and improve the model's predictions compared to the DDPM baseline. NDMs also demonstrate comparable performance to baselines on CIFAR10 and outperform baselines on ImageNet. However, NDMs are less robust when the number of steps is decreased, and they can be combined with LSGM to achieve better likelihood estimation and sample quality. Overall, NDMs with learnable transformations provide additional flexibility in defining the reverse process and can learn simpler generative dynamics. Section 5. Related work. Our work builds upon the foundation of diffusion probabilistic models, which are a type of variational autoencoders, VAEs. Recently, these models have been improved to allow for deterministic sampling and continuous time, leading to impressive results in image generation tasks. However, a common limitation of these models is their reliance on a simple, preset noise injection process that can't adapt to specific tasks or data. To address this, researchers have been exploring ways to make diffusion models more flexible. Several studies have proposed methods to speed up the sampling process from diffusion models. Some have suggested alternative solvers for stochastic and ordinary differential equations, while others have proposed replacing the simple Gaussian distributions used in each generation step with distributions learned by generative adversarial networks, GANs. Other methods include iterative distillation, which reduces the number of steps, and iterative straightening of trajectories. These methods, while altering the generative process, are compatible with our noise diffusion models, NDMs. Some researchers have suggested constructing the data corruption process not through noise injection, but through blurring or other linear transformations. Another approach modifies the dynamics of diffusion models by mapping the data into the latent space of VAEs, hierarchical VAEs, or normalizing flow models, and then running standard linear diffusion. As we show in our tables and appendix, these methods can be seen as special cases of NDMs for specific choices of the transformation function. Inspired by diffusion models, some studies have proposed simulation-free objectives for training continuous normalizing flows. These methods are similar to diffusion models as they reverse a predefined corruption process. Some have extended these ideas and proposed learning the forward process. However, these methods differ from NDMs in that they optimize the forward process to obtain straight generative trajectories, while we optimize a learnable forward process to minimize the variational bound on the negative log likelihood, which doesn't necessarily lead to straight generative trajectories. In another line of research, finite-time diffusion constructions were proposed using diffusion bridge theory to address the approximation error caused by infinite-time denoising constructions. While these methods allow learning forward transformations, they require inferring all latent variables for each optimization step. This breaks the simulation-free paradigm and can make these models expensive to train. In contrast, NDMs allow learning forward transformations efficiently and without simulation. However, NDMs with learnable transformations have their own limitations. Compared to conventional diffusion models, they have twice as many parameters, which results in slower training. For instance, in our image experiments, NDMs with learnable transformations took about 2.3 times longer to train than discrete diffusion probabilistic models, DDPM. But as we show in our appendix, the performance improvements are not due to the increased number of parameters. Another difference between NDMs and DDPM is the importance of using the full objective when training NDMs. A simplified objective, such as the one used in DDPM, which measures how well the model predicts injected noise and doesn't consider the transformation function, can cause the transformation to collapse to zero. This is because it becomes trivial to identify the injected noise through the latent variable. Finally, unlike conventional diffusion, the generative process of NDMs with learnable transformations depends on the parameters of the forward process. Therefore, in the case of learnable parameters, NDMs do not support conditional generation techniques with classifier guidance. However, we can use alternative approaches to enable conditional generation from NDMs, which we will explore in future research.